All right, everybody, thanks for being here. Good to see the room nice and full again. Welcome, everyone, to our 26th Annual Graduate Research Symposium. As the schedule says, we're going to kick things off with two slightly shorter talks from two of our senior graduate students, and then we'll have our keynote lecture, and then the poster session. So since we've already missed the target by a few minutes, I'll just quickly introduce our first speaker, and we'll go from there. So our first speaker is going to be Bratin Sengupta from Professor Yu's group. Professor Yu couldn't be here to introduce him, but he came to the US after his bachelor's degree from NIT in India, did a master's degree at RPI, and then moved here with Miao to finish his Ph.D. here at Buffalo. He's doing great stuff. Big chunk of what he's going to talk about just came out in Science, and so we're all very proud of that. And with that, we'll let him go ahead and present.
Thank you for the kind introduction. My name is Bratin Sengupta, and I'm advised by Professor Miao. So today I'm going to talk about, Today I'm going to talk about how we design membranes to separate molecules by size. So before I start off my talk, I want to give you a brief reason like why we do our work. So I'm going to talk about, I'm going to show you two pictures, and they will tell a contrasting story about why we do our research in the field of membranes. First of all is a picture of an island in Hawaii. It gets like flooded during the summertime because the sea level rises. And the second is another contrasting picture. This is the Lake Mead in Arizona, and every year the lake recedes, the water level goes down by a few meters. And all these are like happening because of the climate change or global warming. And who is responsible for that? Carbon dioxide. And if we look at the carbon dioxide emissions, the carbon dioxide emission is actually associated with the energy use. So what we try to do in our work is to reduce energy use, and the sector we target with membranes is the industrial sector. So if we look at the energy use in the US, it is about like 30 gigawatt hour per year. That is a huge number. And if we break it down, big chunk of it comes from the industrial sector. And if we even look further into the industrial sector, we would see that 55% of that energy is actually used for separating molecule or purifying the product. And how we do that? Most of it is done by phase change, or like the thermal process where you heat up the mixture and you get like a distillate of one of the part. So DOE in its reports actually said that if we can actually replace all of these processes using a membrane or adsorbent, like a physical separation process, you can actually save around 90% of this separation energy, and that is where our work comes in. So when we talk about like membrane separation, like what kind of sizes are we looking at for molecules we separate? Summers have been just around the corner, and everyone had watermelons. The watermelon is at the size of like around 10 centimeter in radius, as a small watermelon, and we are talking about molecules which are 10 order of magnitude smaller than that. So our molecules we want to separate is somewhere here. And if we look into this region, like what are the types of molecule we have, we'll have like three distinct regions. First is the gases, which are the smallest one of the sizes. These are the gases, and then from 4 Armstrong to around 7 Armstrong, we have the liquids. These are the solvents that were generally used in the industry for like different processes. And then there are the solutes, around 7 to 12 Armstrong in sizes. These are usually the homogeneous catalysts, the bigger molecules that we use in the industry to carry out our reaction. The types of separation application that we have for gases are like carbon capture, which is one of the major interest in these days. And there is hydrogen production, where we want to separate one gas from the mixture of them two. The next is the solvents. We want to separate out those solvents, like we have like hexane isomer separation or O-xylene, P-xylene separation. These are very important separation for the petroleum industry. And then for the solutes, we have organic solvent nanofiltration, where we want to reject out or separate out the solvent from the catalyst, or like two catalysts from each other, or two products from each other. Also, like they find application in the food industry, like vegetable oil production. So for today's work, I'm going to focus on these two regions, like two distinct regions. One is from 4 angstrom to 7 angstrom molecule separation, and the next is from 7 to 12 angstrom molecule separation. And before going into my separation and the membranes we do, a brief background about what membranes are. By definition, membranes are a semi-permeable barrier which allows one of the molecule to go through and rejects another molecule. So if you have a mixture of two molecules in the feed side, you put a membrane and you force those two molecules through your membrane, and the smaller molecule goes through the permeate side. This is how you can actually separate out the mixture into its pure component, ideally. So the two main key key component about defining a membrane is actually its selectivity. So selectivity is like how well you can separate out the mixture into its pure component, and the second is the permeance, how fast you can do this process. So traditionally it has been seen when you actually increase the selectivity of your membrane through material design, you compromise on the permeance, or when you try to increase the permeance, you compromise on selectivity. So there is always a trade-off. So this is a trade-off for gas separation, as an example I'm showing, and people are trying to design newer and newer material to actually push this boundary towards the upper right-hand corner. So our goal in our lab is to push the boundary to the upper right-hand corner so that you would actually require lesser of membrane area and lesser footprint in the industry to actually have the membrane technology. So we have rationally designed membranes for these two applications. The first one is a stitched graphene membrane, where we will be using this membrane for hydrocarbon separation. The molecule size is around 4.4 to 7 angstrom, and the second one is interfacial carbon doped metal oxide nanofilms, where we would be separating molecules between the size of 7 to 12 angstrom. First, I will talk about the stitched graphene oxide membrane. So before going into details about graphene oxide, I would like to tell you why we need graphene oxide membrane. So graphene oxide is a 2D material. It has ultra thin dimension of 1 atom thinness, and it has a high aspect ratio. So these are the material that are ideal for actually making ultra thin membranes. So if you can actually reduce the thickness of your membrane, you can actually boost the permeance through your membrane. So graphene oxide is one of the promising choices for making these ultra thin membranes. So traditionally over the last 1.5 decades, what people have been using for graphene oxide membrane is you get the graphene oxide flake, like single flake dispersed in water, you stack them up on a porous material, and this stacked lamellate is actually the separating material. And if you look into the top portion of this graphene oxide from the top, you can actually see the flakes of graphene oxide, and further magnification you can see this graphene oxide flakes, they have a space of between around 8.5 angstrom to 5 angstrom, depending on the synthesis process, between them. And the way a molecule actually enters this laminate is either through the pores. So these graphene oxide flakes have pores or in-plane defects. The molecule can enter through these defects, or either it can enter through the edges into the lamellate. So there are two pathways of molecules to enter the graphene oxide flake. So how are molecules separated by this graphene oxide membrane? Suppose you have a stacked membrane which has a d spacing, or the distance between the two stacked layers is around d. And if you have two molecules you want to separate, so you need one of the molecules to be larger than this d spacing, so that the molecule cannot enter the membrane, and the other molecule to be smaller so that it can enter the membrane. So what happens if you have both of the molecules smaller than the d spacing? You end up having both the molecules enter the graphene oxide lamellate, so you cannot achieve any kind of selectivity. So to achieve any kind of selectivity between smaller molecule, it's very challenging to use graphene oxide membrane, and what we need to do is to eliminate this transport pathway so that you can use this transport pathway to make sure that we can control this transport pathway and determine which molecule we would allow to enter this stacked membrane. So to do this, we came up with the idea of stitching graphene oxide membrane. So what is actually stitching graphene oxide membrane? So if you put up this graphene oxide flakes, stack them together, we know that the graphene oxide have high density of functional groups, like the hydroxyl groups or the carboxylic groups, along the edges of the graphene oxide flake or at this defect site of the graphene oxide flake. So we choose a chemistry, a vapor phase chemistry called molecular layer deposition that actually grows on this hydroxyl group. And this material is dense in nature. So when this material actually grows on this hydroxyl group, they end up growing at the edges of this graphene oxide flake and at the pore mouth of the graphene oxide flake. Since these are dense material and they do not allow any kind of permeance, we end up eliminating the transport pathway through the edges of the graphene oxide flake. And this modified defect becomes actually, they become selective, and they allow certain small molecules to go through into the graphene oxide flake, the stacked graphene oxide flake, and they actually prevent the larger molecule from entering. And this is the basis of our separation through the stitched graphene oxide membrane. I'll give you more evidence like how we can actually do this kind of, how we confirm this structure. So before that, I want to give you a brief idea about what is molecular layer depositions, or MLD. So if you start off with the surface having a lot of OH groups, so this represents the edge sites of the graphene oxide flake. And if you introduce a precursor called titanium tetrachloride, this will start reacting with this OH group. And you will have this oxygen titanium bond with 3 dangling chlorine groups hanging out, and these are very reactive chlorine groups. And then if you introduce an organic precursor, which is ethylene glycol in our case, they will start reacting with this chlorine group to form this network structure. This network structure is actually dense in nature and do not allow any permeance of solvent. And we can keep on repeating this step in an automated system n number of times as we wish. So each of this cycle is called one cycle of MLD, and we can control the number of cycles we want to control the growth on our graphene oxide. So what actually the MLD does to graphene oxide? The first thing is MLD actually seals the edges of graphene oxide. So if we look at a flake of graphene oxide under AFM, it has a constant height of around 1 nanometer. So the surface is absolutely flat. And then on a single flake of graphene oxide, if we do around 5 cycles of molecular layer deposition, we end up seeing there is a growth at the edges, growth of material, which is represented by this increase of height in the material. So if this is an edge, you will have the material growing at the edges of graphene oxide. The pores within the flakes are too small to actually see in the AFM resolution. So this is one thing, and if we have a stacked graphene oxide membrane, this translates to something like this. You will have the like the graphene oxide flakes on the top surface, and this material will go along the edges of those flakes to actually stitch them together. So you have like small pieces of graphene oxide flake as if you are stitching them together into a large continuous sheet. And there would be pores within this structure which allows the permeance of molecule through them. And the second thing of this molecular layer deposition actually does is solves a very traditional problem of graphene oxide membrane. So you have I told that the graphene oxide flakes, the distance between them is around 8 angstrom in size, but during permeation in solvents or in water, they tend to like swell up and the size between them actually increase. People have tried to do cross-linking to stabilize them. So MLD actually stabilizes them because there are some basal, at the basal plane, there are some functional groups, they end up cross-linking with each other. So we look at the XRD pattern to see what is the distance between 2 graphene oxide flake. And if we see for 0 cycle MLD, this is the pristine graphene oxide, in the wet state or in the permeation state, the despacing actually increases a lot. And after doing around 5 cycles of MLD, we stop this increase of this or this swelling. So we believe that there is some amount of cross-linking between the flakes of graphene oxide. So with this, we go up and look at the permeation of the small hydrocarbon molecules through this graphene oxide membrane, the stitched graphene oxide membrane. For different cycles of MLD, this number represents the number of cycles of MLD. We can see that the linear hydrocarbon, the smaller one, permeates around 2 order of magnitude faster compared to the larger branched one or the cyclic one. And there is some amount of tunability between the single branch and the monobranch alkanes. To give you a better perspective of what actually happens during the stitching, I'll show it in a schematic. Suppose this is a graphene oxide membrane and you have 3 molecules, the small linear one, a medium-sized 2-branched one, and a 3-branched one, which is the largest of them all. In a pristine graphene oxide where you have the edges open and the big pores which are present, you actually find that all the 3 molecules enter the membrane and you have a viscosity-dependent permeance to this membrane. This kind of permeance have been reported by a lot of literatures where they show that the permeance of solvents in a graphene oxide membrane actually depends on the viscosity. But what happens if we do just 10 cycles of MLD? We end up sealing these edges so that we can actually cut out this molecule, the larger molecule. So if you see, like if we move from if we look at the selectivity between these 2 molecules, and if we move from 0 cycles MLD to 10 cycle MLD, after 6 cycles MLD, there is an increment of like 250 times of increment of this selectivity. So this can only happen if you actually block out these pathways. And then if you keep on increasing the number of MLD cycle, what happens is that you constrict these pores. So if you look at these 2 small molecules, among the smallest molecule is the N-hexane. Its permeance decreases by 0.3 times when you constrict the pores. But for the medium-sized molecule, when you constrict the pores, its permeance decreases by 400%. So we show that this method actually tunes the in-plane pores of graphene oxide. So this gives us an idea like we can actually make ultra-thin membranes where we can actually separate out molecules, small molecules based on their size, where all the molecules are below the d-spacing of graphene oxide sheet, graphene oxide interlayer. So what we believe is that the permeance we get through our membrane during mixture separation is due to the ultra-thin nature of our membrane. So for reported membranes for pressurized permeation of this kind of hydrocarbons, our membranes provide at least 1 to 2 order of magnitude higher permeance through our membrane because of the ultra-thin nature of the membrane, because of the material we choose to fabricate this membrane. And what we propose for the structure of this membrane is something like this. We have the porous material, which is non-selective. On top of that, when you start depositing graphene oxide, we have like a very messy structure, and the structure slowly becomes lamellar in nature. And after we do the stitching, this stitching mechanism actually stitches the first few layers of the structure. We confirm this structure by a series resistance model as well. So we have a membrane that separates molecules, hydrocarbon molecules based on the sizes. What we can use this membrane for? One of the best examples where we can use this membrane is actually fractionation of naphtha. So if you look at the distillation column in the petroleum industry, the top product is a naphtha, which has a research octane number of around 50. So it has the linear hydrocarbons, a huge amount of linear hydrocarbons, the branch one, the cyclic, and the aromatic. What is traditionally done in the industry is to take this naphtha into a catalytic reformer. And this catalytic reformer converts the linear hydrocarbon into the branch ones or cyclic ones. And this is what we actually get as the gasoline. But what we propose is that we would take this light naphtha from the petroleum, the top product of the distillation column, into a membrane unit using our stitched graphene oxide. So this membrane unit this membranes would permeate the smaller hydrocarbons through them, and these smaller hydrocarbons usually have the low octane number, and we will feed only this fraction into the catalytic converter. So this actually reduces the load of the catalytic converter and actually reduces the footprint or the energy requirement for the catalytic converter. So you are not feeding unnecessary feed into the catalytic converter. What interesting is that this membrane also reduces some of the sulfur containing compounds. And if you can reduce the sulfur containing compounds, you actually minimize the risk of poisoning the catalyst present in the catalytic reformer. And the retented side, what does not go through this membrane, are the high octane number product, the larger branched one. You can actually mix them together to get your final gasoline blend. And depending on the requirement of the sulfur limit, you probably have to do some kind of hydrodesulfurization to meet the environmental requirement for your gasoline blend. So what we started off doing is we took a mixture of 9 components, a complex naphtha mixture, synthetic mixture of these components based on the varying sizes, and we ran them through our membrane, and we see that the smaller hydrocarbons, the linear one, get enriched in the feed. Whereas the larger one, the single branch or the double branch or cyclic or aromatics, their amount get lowered in the feed. So they are diluted in the feed. So we can actually produce a permeate stream containing usually most of the linear chain hydrocarbons. We ran this process for over 100 hours. We can see that we got some stable permeance through our membrane over 100 hours of operation. And the thiopene limit, so this is the sulfur compounding compound, its composition came down from 115 ppm to around 35 ppm. So we have been significantly able to reduce the sulfur content from the naphtha. And if you look at this two line, this is the research octane number of the mixture feed. And if you have the same amount of linear hydrocarbon, this is the minimum research octane number that you can obtain. And through our process, we reach somewhere up to like 95% of the minimum permissible limit. So we can say that this kind of membranes can be actually used industrially if we design a process around these membranes to reduce the load of catalytic reformer. To sum up my work in this region, that we have developed a one-spot synthesis method which seals the edges of graphene oxide, locks the flakes together, and makes the in-plane pores selective. Like you can tune the in-plane pore. And we have achieved size selective permeation of hydrocarbon, small hydrocarbon between the size of 4 to 7 angstrom through this membrane. And we have also demonstrated our RON-based fractionation of complex synthetic naphtha. And so for the second part of the membrane, I'll try to keep it short. We have developed a newer material. We borrowed the same chemistry of molecular layer deposition. We took it into a liquid phase. And we have developed a material called carbon-doped metal oxide membranes. So the target separation for these membranes are molecules between 7 to 12 angstrom. So to separate out molecules in the industry for 7 to 12 angstrom, you need to design a material which can actually separate molecules based on size. So that is the first criteria. Suppose you make a material that actually have pores in that range and you are like, okay, I have my material. Now what I have to do to this material to actually take it into the industry and scalably use them? You have to turn this big slab of material of like say 200 micron into something around 100 micron. So you have to make a composite membrane out of it to make it actually industrially relevant and usable. And there is no better way we have seen it from the literature and from like industrial success than interfacial polymerization. And it began in the 1970s, and this kind of membrane, like from DuPont, these are FT30 membrane. In this kind of interfacial polymerized polyamide membranes are still the gold standard for industrial desalination application. But the problem with them is you cannot use them for solvent separation. So if you have a solvent at a high temperature or even at a low temperature, this materials, polymers just dissolve in it. And another problem is that you have the non-rigid pores within this polymer, and they get compressed with the pressure when the pressure is applied through the material. And this kind of material actually suffers from the trade-off of selectivity and permeance. So what we try to do is find an analogous inorganic material to this to this interfacial polymerization technique. So this is our goal. And the next thing is to have a material where you can actually get high permeance through the material. So you can make it thin, but how to achieve higher permeance through this material? So to look at this, we looked at to get around this problem, we looked at the very classical Huygens-Poiseuille equation. So if this is the Huygens-Poiseuille equation, you can actually break it up into two parts. The first part is the solvent property, so the permeance through this membrane actually depends on this solvent property. And this second part is actually the membrane property. And if we can further break this down, we can actually find there are two independent properties that we can actually work around with. First is the membrane thickness. So I talked about making membranes thinner in my last work. And then there is another untapped area where people did not work much, is the tortuosity normalized pore density. So if you have a higher density of pore in your material, you can actually achieve high permeance. And looking into the literature over the last 1 decade, people have been trying to make thinner and thinner membranes. The problem with making thinner membranes is scalability. If you try to make a 1 atom thin membrane, it's very difficult to make centimeter square or even meter square of those membranes. So what we try to tune in our new material is this factor. So we want to increase the pore density of our material to push it to a limit where we can actually have higher permeance without actually making membranes very thin. So that with that goal, we set out to fabricate our membrane. We call this carbon-doped titanium oxide. Titanium is one of the metals, so we call it a CDTO nanofilms. So we actually fill up the pores of a support membrane, which has large pores, with an organic precursor, and then we introduce the vapor of the inorganic precursor, the titanium tetrachloride, and it reacts to form the dense material as I talked about in my last work. And if we calcine those material, they generate pores. To have a better look at what happens at that interface is that we have two phases. Ethylene glycol phase, which is the liquid phase within the large pores of this material, and we have in the vapor phase titanium tetrachloride. And if these two material react, so the chemistry is borrowed from MLD, which is a very known chemistry. And if these two react, they actually generate an organometallic hybrid material like this. And the same thing would happen when they react at the interface. They would generate an organometallic hybrid nanofilm at the interface. And this material is dense in nature. So we call it the dense OHF. And there is no permeance of any solvent or gases through this material. And once we start taking out the carbonaceous part or the organic part from this material, we start generating pores within the material. And then these pores turns out to be very selective in nature. It blocks out the larger molecules from going through and allows the smaller molecules to go through. So this is the basis of our carbon-doped metal oxide membrane. So to look at how the film forms over time, we look at the permeance of methanol through the support membrane. So for this, we have taken a hollow fiber support. the methanol permeance is over 700 LMH per bar, which is a large number. And then after at 0 minute of reaction, this is how the support looks like. You can see the large pores in them. After 1 minute of reaction, you start shrinking the pores as you start growing the film. And around 3 minutes, you only see like very few small defects. At around 5 minutes, you see no permeance of methanol and you get a completely dense film. So on calcining this dense film, you end up actually having the porous material like with the nanopores in them. So we looked at the permeance of different solvents through this nanofilm, and this is a nanofilm formed, these are two nanofilms formed on anodic aluminum discs. These have like higher permeance, so you will see higher permeance through this support. And all the solvent permeates through this support depending on the viscosity only. So it only depends on the viscosity of the solvent that you are permeating through. And we did the same thing on a hollow fiber support, and hollow fibers are the ones which you usually use in the industry. So the same 6 solvents maintain the same viscosity dependent permeance. What we did next was take a 7th solvent, which is DMF. DMF is known to be a very corrosive solvent, and it like dissolve most of the polymers that we use for making membranes. And what we did is, after looking at the permeance of DMF at room temperature, we started increasing the temperature at which we conduct the permeation experiment. And what we see that at increasing temperature, the viscosity of the DMF reduces, and it follows the similar permeation trend as it followed for the other solvents. So increasing temperature actually maintains the structure of the pores through this material. So we want to look at if it can still selectively separate out molecules at higher temperature or not. So we went for a solution of DMF and rose bengal at different temperature up to 140 degrees centigrade. We can see stable separation of rose bengal from DMF. So this indicates that the membranes are very stable at high temperature. So this allows us to use this membrane for industrially relevant application where you have a solvent, where you have to operate the membrane at a very high temperature. For example, if you want to synthesize something at high temperature and want to separate out the product and the catalyst, you don't have to cool down the reactant and the mixture of the reactor and then use a membrane. You can actually use it at the same reaction temperature. This helps to reduce a lot of energy consumption in the industry. So to further look into that, you have to have a membrane with a lot of different pore sizes because you have different sizes of molecules. So to generate pores within the membrane, we actually need to calcine those OHF, the dense material, at around 250 degrees centigrade. You can do this calcination at 2 different environments, either in air or nitrogen. So air releases more carbon from the material and you end up having larger pores. And nitrogen releases lesser carbon. It retains more carbon and you end up having smaller pore. So carbon is the key to determine the pore size of this material. So, and we call this amount of carbon remaining as the carbon doping of this material. So these are some of our simulation results. The colored region actually shows the pores within the material, and the numbers on the top actually shows how much carbon is retained within the material. We call this the carbon doping. And if we look at the porous behavior of this material with the carbon doping, we can see like if you reduce the carbon doping, you can have higher porosity through this material and you will have high surface area. And this actually gives us an idea how the pores are getting tuned within this material. So if you have this material with the purple dots as the carbon, if you start removing more and more carbon, you end up getting larger and larger pores. So by tuning the carbon, we can actually have a series of membrane. And how do we do that? We either alter the amount of carbon we remove from the material or alter the amount of carbon we have in the initial material. We alter the carbon removal by changing the temperature at which we remove the carbon or by changing the environment in which we remove the carbon. To alter the initial composition, we add a little bit of water to reduce the carbon amount in the initial film. So doing that, we can actually get a series of membrane going from a molecular weight cutoff. This actually shows the pore size of the membrane from 200 Dalton to around 1000 Dalton, and this represents a pore size range of around 7 angstrom to 11 angstrom in size. So we have a series of membrane as we proposed between the 7 and 12 angstrom size range. And the steps change is only 100 Dalton. So why do we have high permeance through the membrane? So again, we go back to the Huygens-Poiseuille equation. So for this equation, we know all the terms in the equation. So if given all the terms we know in the equation, we can actually calculate this epsilon by tau, which is the tortuosity normalized pore density. And we found out that the tortuosity normalized pore density, the pore density of our material is significantly higher compared to the material that is already existing in the literature for this kind of material. And one thing that is important to note here is when you go to the lower and lower pore size, it becomes very difficult to have a material with high pore density. So the small pores tend to actually like merge together to become larger pore. So what you need for your material is that to have a very high mechanical stability so that the small pore can retain their structure and not merge together. And we measured the mechanical stability with the help of our collaborators for this membrane, and we found them to be very high in the order of like something in the range of like diamond-like carbons or carbonaceous materials. So this allowed us to actually have high pore density at the low molecular weight cutoff range. And this is what translates to actually having high permeance compared to other membranes in the literature. But you will be astonished to see that there is one black dot which is kind of outlier. So this is a single atom thin graphene membrane. So you have to make a single atom thin membrane to actually match up like the permeation of a solvent of a material having a higher pore density. And compared to this material, our thickness is around 70 times more. So we can actually generate high permeance by increasing the pore density. So we show our avenue of like not making membranes ultra thin so that you cannot scale them up. So with this, we look into the production of boscalid. So you have like 3 molecules which reacts to form these larger molecules in a presence of solvent like DMF at 80 degrees centigrade, and you have a large catalyst. So we planned on designed a membrane cascade system where the first membrane has larger pore size and the second membrane has smaller pore size. We took the feed out of the reactor and fed it to the first membrane. The first membrane actually separated out the large catalyst, and we can recycle it back into the reactor. And the permeate of this first membrane are this product and the small molecules which are the reactant. This is fed into the second membrane, and in the second membrane actually rejects out the larger product compared to the feed, compared to the reactant, and the reactant and the solvent we can actually send it back to the reactor. So we ran this membrane operation for a period of 100 hours for a stability test at 90 degrees centigrade. We see a stable permeance through the first and the second membrane, where the first membrane separates most of the catalyst and it cannot reject out the reactant and the product, whereas the second membrane separates out most of the product and it cannot reject out most of the reactant. So the permeate of this can be sent back to the retentate. And if we look at the different profile of the concentration, the permeate coming out of the first membrane is rich in reactant and product, whereas all the catalysts have been stripped off. And the permeate coming out of the second membrane is actually rich in permeate, and the product has been stripped off. So we show over 100 hours of stable performance in DMF at 90 degrees centigrade, which is close to the synthesis condition of boscalid. So to summarize the result for this work, we actually took the chemistry, borrowed the chemistry from MLD and developed an ultra-fast process of making thin film composite membrane by interfacial polymerization. Our material showed one of the highest pore density due to the mechanical properties of it. And we show that the pores are tunable by changing the amount of carbon within the pore. And these membranes are actually stable at high temperature and high pressure and in harsh solvent. With that, I would like to thank my group members, my professor, Professor Yu, and my collaborators at RPI, Vanderbilt University, and UB, and the funding agency who funded this work, the UB Startup Fund and NSF. And this is the photo of our group we took from the last grad symposium. Thank you. With that, I would like to have
a question. We did get a little bit of a late start, so maybe just 1 or 2 quick questions if you have burning questions. I don't want to discourage you. Now you think you have to be the most important question.
Burning questions. Great presentation. Thank you. So you're in the first part of the project, the blocking, the stitching. You presented as if you're it's sort of all or nothing. I block this space and then nothing goes through, or it's open, or something goes through. There may be a place in the middle where you could use chemistry of those stitching groups to
make them selective. We thought about that initially, that if we can use the chemistry to make those blockages selective, But it seems like within that pore size range, it's very difficult to like come up with a chemistry that like prevents only some of the molecules from entering. And if that could have happened, that would like increase the permeance even higher, because right now we are eliminating completely one of the pathway, which ideally we won't like to do. We would like to make it selective as well, but we cannot like make it selective. That's one of the limitations.
Thank you.
Great question. Oh, sorry, great presentation. Actually, great questions. I'm following up a similar way. So when you grow the layers on the edge and inside of the pore, did you control it? Because in one of your figures, you showed the thickness of your growth on the edge is thicker than the growth on the edge.
Yes, so the number of MLD cycle actually tells, like you can control it by the number of MLD cycles. So if you have 15 cycles, you grow a certain amount at the edges, and the amount of hydroxyl group present actually tells you how much you can grow. So in theory, for a graphene oxide flake, you have maximum highest density of hydroxyl group around the edges, followed by the larger pores and followed by the smaller pores. So it will preferentially grow at the edge and then the larger pores, and then the smaller pores. Even some of the small pores might not even have hydroxyl group. You cannot even block those pores.
Okay, thank you.
All right, let's thank